Alright, so in the last section we discovered how to find the convergence or divergence of alternating series. Right, so we looked at the alternating series test, which was great because now we can decide that, even though we don't have something that has all positive terms, we can still prove that it converges, which was difficult to do with some of our earlier tests, like the comparison test, for example. Well, now we're going to talk about some things called the absolute convergence and conditional convergence of alternating series. So for now, I kind of want you to just forget those two big words that I mentioned, or two big terms, and let's just look at something real quick. If I have some series built off this sequence A sub n, then we can consider the corresponding series where we just take the absolute value of every term. Right, so this would be the absolute, this is the series where we do the absolute value of A1 plus the absolute value of A2 plus the absolute value of A3, and just keep on adding in this manner. So in 11.5, we decided that, okay, both of these series right here converge by the alternating series test. And so now I want to look at, okay, well, what happens when I take the absolute value of these series? So for example 1, if I look at this is going to be, so let's just kind of think about what this would be if I'm plugging in values for n. So if I plug in n equals 1, then I'll have the absolute value of negative 1 to the 1 over 1. Now if I plug in 2, we'll have the absolute value of negative 1 to the 2 over 2. And for 3, we'll have the absolute value of negative 1 to the 3 over 3. And so on, right? Well, this is going to look like 1 plus 1/2 plus 1/3, and so on. And so we can really say that this is just the sum from n equals 1 to infinity of 1 over n. Because what happens here is we're taking the absolute value of everything, so this negative 1 right here no longer matters. And the power that we take for 1 isn't going to matter because 1 to any power is going to give us 1. So that's why I'm rewriting this as 1 over n. Okay, well, we know that this thing right here diverges by our p-series. So then we can say that what we started off with, right, the sum from n equals 1 to infinity of the absolute value of negative 1 to the n over n, this thing diverges, right? So I took this series, right, without the absolute value, we know that this thing converges. We showed that in 11.5. However, when I take the absolute value, now it diverges. So let's see if that happens in example 2. Well, in example 2, when we take the absolute value, this is going to become the sum from n equals 1 to infinity of, remember, this negative 1 to the n is just going to become positive 1 when we take the absolute value. And then n squared will stay as n squared. We know that this converges by our p-series. So here, we started off with something that without the absolute value, it converges. And then with the absolute value, it converges. So what we say is that this thing, the sum from n equals 1 to infinity of, we'll take away our absolute value, negative 1 to the n over n squared. Since we took the absolute value, and it still converges, we say that this thing is absolutely convergent. Similarly, since this right here diverged, we can say that what we started with, right, so if we take away the absolute value, we can say that negative 1 to the n over n is what we call conditionally convergent. So again, if we have some alternating series that converges, and then we take the absolute value and it diverges, then we call it conditionally convergent. Now, if we have some alternating series that converges, we take the absolute value and it still converges, then we say that it's absolutely convergent. Right? And so that's what this definition right here is saying. It's saying that a series is going to be absolutely convergent if the series with the absolute value converges. And then if this latter thing, right, if this part right here doesn't converge, then we say that it's conditionally convergent. Now, the reason I'm using alternating series right here is because if you have some series of positive terms and it converges, then by default, it is going to be absolutely convergent because that absolute value won't affect it. That's what this note right here is saying. Okay. Another quick thing, this part right here that looks like it's kind of screaming at you. Sometimes people will neglect to say that something's absolutely convergent. When we say that something is just convergent from now on, we're going to mean absolutely convergent. So from this point forward, if we say that a series is convergent, then we are saying that it is absolutely convergent. It's just the way that mathematicians are lazy and, we don't want to write out these extra letters from the word absolutely. Now, if you want to, you can skip past this explanation that I'm about to read off. Or if you're interested, you can listen to this. But this is telling you why do we care about absolute versus conditional convergence. So infinite sums are kind of weird in the sense that sometimes they're not like our finite sums. So imagine you have 5 real numbers, something like 1, 2, 3, 4, and 5. If I add them together, right, if I do 1 plus 2 plus 3 plus 4 plus 5, we would get 15. And no matter how I add those numbers together, right, I can rearrange them. I could do like 2 plus 3 plus 1 plus 4 plus 5. No matter how I rearrange those, I'm always going to get 15. This is because the addition of real numbers is commutative. But there are times where we take a sum of infinitely many real numbers, and you can rearrange the terms and get different sums, right? So I'm just changing the order that we're adding and somehow getting a different number. This is the difference between absolutely and conditionally convergent. If something is absolutely convergent, right? If it's absolutely convergent, then any rearrangement of the terms being added will give the same sum. Now, if something is conditionally convergent, then that means that if we change the order sometimes, we will get a different sum. For an example of this, you can check out page 742 in the textbook, or you can ask me about it in office hours, and I'd be more than happy to show you one of these conditionally convergent examples where I can rearrange things and give us an answer that we would not expect to get. Okay, now let's continue on and actually start showing, are things absolutely conditionally convergent, or are they just divergent? Okay, so the first thing that we do whenever we're asked a question like this is we should probably decide, is this going to be a convergent case or is this a divergent case? Well, if I look at my test for divergence here, it doesn't seem like it's going to be helpful. And in fact, if I'm just looking at this thing and ignoring that -1, this looks like a p-series that is going to be convergent. Furthermore, we could use our alternating series test right here and show that this series right here is indeed going to converge to something. But now we want to find out, okay, is it absolutely or conditionally convergent? So what I'm going to do is I start by taking the absolute value of all of these terms. And so when I write this, I'm saying that a sub n is equal to -1 to the n over n square root n. So then the sum, well, that -1 to the n is just going to become 1 because of the absolute value. So this will become 1 over n times square root n, which is n to the 3/2. And we can say that this is convergent by the p-series. What that tells me, so that means that the sum from n equals 1 to infinity of a sub n is going to be absolutely convergent. And I'm going to try to not be lazy right now, so I'll write out absolutely convergent instead of using the shorthand of just saying, oh, well, it's convergent. Okay, so we took the absolute value here. We got that this new series is convergent, so that means that our original series must be absolutely convergent. Okay, now let's look at example 4. Again, we can prove that this thing is going to converge by the alternating series test. And so now I want to find out, okay, well, is it absolutely convergent or conditionally convergent? So I'll look at the sum from n equals 2 to infinity of the absolute value of a sub n, where again, this entire thing right here, this is my a sub n. And so this is going to be the sum from n equals 2 to infinity of 1 over n times the natural log of n. And so here, what I'm going to use is the integral test, right? So we look at the integral from 2 to infinity of 1 over x ln x dx. And I'm going to use a u substitution here. We'll do u equals ln of x. And so that will give me, so we know this is an improper integral. I'll rewrite it as a limit. So we have the limit as t goes to infinity. I have to redo my bound. So this will be ln of 2 to ln of t. When we do our u substitution, we should get 1 over u du. All right. And so then this will give us the limit as t goes to infinity of the natural log of u from evaluated from ln of 2 to ln of t. All right, so then this gives me the limit as t goes to infinity of, let's see, this would be the natural log of the natural log of t minus the natural log of 2. Well, this first part right here, since t is going to infinity, this is going to go to infinity. And so we get that this integral diverges. And so remember, the integral test says that if this integral diverges, then our original sum must also diverge. So this means that it doesn't converge absolutely. And so now what I want to do real quick is actually prove that it does converge conditionally. Right? So I'm putting here converges conditionally with a question mark, meaning, okay, how do we show that it converges conditionally? Well, to show that it converges conditionally, all I need to do is show that our original series, right, this up here, I just need to show that this converges. To do that, we'll look at the alternating series test. Okay, so we know that, so here we'll have the sum from n equals 2 to infinity. We could rewrite this as negative 1 to the n times 1 over n times the natural log of n. Right, and so then this piece right here, we're going to call this b sub n. And so then the alternating series test says that we need to check that b sub n is positive. Well, ln of n is always going to be positive since n starts at 2. and n will be positive, so we definitely know that b sub n is greater than 0. The next thing we need to check is that this is decreasing. We've shown before that this is decreasing, so b sub n is decreasing. And then the third thing we need to show is that this limit goes to 0. Well, our denominator here will be going to infinity, so we can say that the limit as n goes to infinity of 1 over n times the natural log of n is going to be equal to 0. And so now we can say, the sum from n equals 2 to infinity of negative 1 to the n over n times the natural log of n converges conditionally. All right, so now let's take a look at example 5. For example 5, the first thing I want to note is that I cannot do the comparison test on this, right? If I'm trying to solve for the convergence or divergence of this series right here, I can't do the comparison test because sometimes our cosine function is negative, which means that our terms won't be strictly positive. So what I'm going to do is I'm going to look at the sum from n equals 1 to infinity of cosine of n over n to the fourth, right? And so I'm going to look at the absolute value of this. You should check that this series is actually convergent, right? To look at that, we can look at the fact that this denominator is going to go to infinity. So this sequence is going to converge to, the sequence does tend to 0. So by the alternating series test, we can say that this is actually convergent. But now when we look at this, this would be the same thing as the sum from n equals 1 to infinity of the absolute value of cosine of n over n to the fourth, right? I don't need this absolute value on n to the fourth because n's always going to be a positive number. So the absolute value doesn't really affect that. Well, we know that the absolute value of cosine of n, this has to be greater than or equal to 0 because we have that absolute value, right? So now, normally we would say cosine of n is greater than or equal to negative 1. But since we're taking an absolute value, we can say that it's going to be greater than or equal to 0. And it's going to be less than or equal to 1. So now we have all positive terms, which means once we've taken this absolute value, when we're looking at absolute convergence, we can look at using a comparison test. So we can say that this is less than or equal to the sum from n equals 1 to infinity of 1 over n to the fourth, right? And that's because this absolute value of cosine of n has to be less than or equal to 1. Well, this is going to converge by the p-series, which means that this original part, right, this right here, since it's smaller, it must also converge, which tells us that the sum from n equals 1 to infinity of cosine of n over n to the fourth, it's going to converge absolutely by the comparison test, right? I can't just start off, remember, in order to use this notion of absolute convergence or conditional convergence, we need a series that is convergent, right? So we can't use the comparison test on this. However, when we take this absolute value right here, Now we can use our comparison test. All right. Now that we've talked about this, we're going to talk about another way of finding absolute convergence or divergence. And this is going to come from something called the ratio test. Okay. So the ratio test says that if you take a limit as n goes to infinity of a sub n plus 1 over a sub n, and this is equal to some finite number L that's less than 1, then the series is going to be absolutely convergent. We know this is going to be a finite number, right? Because we have absolute value right here. Whoops. I made that really disgusting. Sorry. We have an absolute value right here. So whatever this limit is, it certainly has to be greater than or equal to 0, right? It can't be negative because we have that absolute value. So we're just saying that L is less than 1, but of course it's going to be positive. So if we end up in a scenario like this, then we can say that the series is absolutely convergent. Now if that L ends up being greater than 1, right, some finite number greater than 1, or even infinity, then we can say that our series is going to be divergent. If it is equal to 1, then the ratio test is useless to us, and we say the ratio test fails. Now, one of the tricky things about what we've been encountering lately is when do I use all of these different tests? So we know when to use telescoping or geometric series because we kind of figure out, okay, well, does this have power of n? Well, then it might be a geometric series. Do we have terms canceling out? Well, then it might be telescoping. And we've kind of looked at when we should apply various other tests. So now I want to look at when do we apply the ratio test. We generally use the ratio test whenever we have factorials, right? So something that looks like n factorial or n plus 1 factorial, something like that, or exponentials. And exponentials are going to be stuff that looks like x to the n for some x value. So something like 3 to the n, or, even pi to the n, right? Some constant number to the nth power. Okay, so let's look at example 6. We want to determine whether this is absolutely convergent, conditionally convergent, or divergent. So when I see that we've got this 3 to the n, we've got a negative 2 to the n, and I've got an n cubed, right? This n cubed right here is what's telling me I'm probably not going to use geometric series, right? Because in geometric series, we always have constants to some power. We don't have our n to some power. So what I'm going to do is I'm going to look at the ratio test because I have exponentials in here. So this part right here, this is going to be my a sub n, which means that a sub n plus 1, this would be 3 to the n plus 1 over n plus 1 cubed times negative 2 to the n plus 1. All I did here was I replaced all of the n's with n plus 1. Okay, so now we should have the limit as n goes to infinity of a sub n plus 1, so that's going to be 3 to the n plus 1 over n plus 1 cubed times negative 2 to the n plus 1. Right, so we should have a sub n plus 1 divided by a sub n. So divided by 3 to the n over n cubed times negative 2 to the n. And so what's going to happen here is that this piece is going to multiply up to the top. This piece will multiply to the bottom. And so this will give us the limit as n goes to infinity of 3 to the n plus 1 times n cubed negative 2 to the n over n plus 1 cubed times negative 2 to the n plus 1 times 3 to the n. Right? Now, I know I haven't put the absolute value in yet, right? That's part of our ratio test. It should be the absolute value of a sub n plus 1 over a sub n. I'm going to put that in at the end just because I want you to see the algebra that's happening here. So notice I have a 3 to the n plus 1 being divided by 3 to the n. Well, that would give me, if I subtract exponents, then this is going to be just 3 left on top, right? Because n plus 1 minus n will give me just 1, so this is 3 to the 1. This n cubed isn't going to get canceled out. But I have a negative 2 to the n up here, and a negative 2 to the n plus 1 down here. So that means that I'll have a negative 2 left on bottom. Right, so it'll be negative 2 times n plus 1 cubed. All right, and so using our highest power rule, this will give us 3 over negative 2. So now I'll put my absolute values in. Right, so absolute value, absolute value, absolute value, and then we need to take an absolute value of this. So for our answer for this limit, that gives us 3/2. Well, what's important to notice is that 3/2 is greater than 1, which means that our original sum from n equals 1 to infinity of 3 to the n over n cubed times negative 2 to the n, right? That means that this diverges by the ratio test, which I'm going to abbreviate as RT, which does not mean retweet. All right, now let's look at example 7. So from here on out, I'll start putting absolute values in at the beginning because hopefully now we'll be more accustomed to seeing how this algebra is going to work out. But feel free to write it out if you need to see how everything is working out. So here, this is my a sub n. So then a sub n plus 1 would give us, let's see, this would be n plus 1 to the 10th times negative 100 to the n plus 1 over n plus 1 factorial. So then we'll have the limit as n goes to infinity of a sub n plus 1. Right, so that would be n plus 1 to the 10th times negative 100 to the n plus 1 over n plus 1 factorial divided by a sub n. So n to the 10th times negative 100 to the n over n factorial. And then we'll take our absolute value. Right. The only reason I'm using green is to make sure I don't lose track of these absolute value signs in this mess of an equation. So now just like last time, I'm going to multiply things. So this n factorial will need to come to the top. And this n to the 10th negative 100 to the n will need to come to the bottom. Okay, so this is n plus 1 to the 10th negative 100 to the n plus 1 times n factorial over n plus 1 factorial times n to the 10th times negative 100 to the n. Okay, so there's something we need to remind ourselves about, which is how does factorial work? So imagine I have something like 5 factorial over 6 I want smaller numbers. This is gross. Imagine I have something like 4 factorial over 5 factorial. This is 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. So all of these can cancel out, and we'll be left with 1 over 5. Well, notice that's just, we're canceling out this 4 factorial and leaving everything that came after 4, right? So We canceled out everything up until 4 and then left the 5 because it comes after, right? And so the key thing here to note is that n factorial over n plus 1 factorial is equal to 1 over n plus 1. Okay, so using that, I have a n factorial up here, and n plus 1 factorial down here. So that'll give me the 1 over n plus 1 factorial, or sorry, 1 over n plus 1. So I'll have an n plus 1 down here. Well, then I've got a negative 100 to the n plus 1 on top, and a negative 100 to the n on bottom. So that'll leave me with a negative 100 on top. And then I'll have n plus 1 to the 10th on top. And a n to the 10th on bottom. Okay, so I'll need to take an absolute value of this. Now, the absolute value will just get rid of this negative on the negative 100. And using our highest order rule, what's happening is that when this and this multiply out, we're going to get an n to the 11th on bottom. But the highest degree we'll have on top is going to be an n to the 10th. So this is going to go to, right, so by highest degree, so I'll write HD, I guess. This will be the limit as n goes to infinity of 100 n to the 10th over n to the 11th. All right. And then by L'Hopital's rule, we can get that this is going to go to 0. And 0 is less than 1, which means that our series converges absolutely by the ratio test. All right, now let's take a look at example 8. So, speeding along here, we'll have the limit as n goes to infinity of the absolute value. I'll put this in at the end. So we'll have a sub n plus 1. I'm going to need more space. A sub n plus 1 would be 2, right? I'm replacing n with n plus 1. So we'll have 2 times n plus 1 factorial over n plus 1 factorial divided by, now we should just have a sub n. So this will be 2n plus 1 factorial over n factorial. Right. Now I'm going to put the absolute value sign in here, but it's going to go away immediately because n starts at 1, and so our factorial means we're just multiplying positive numbers, so there's really no need for an absolute value right here. Right, so this is an example of, we use the ratio test on other things than just alternating series, right? This is one of our factorial examples where we're using the ratio test. So we've got the limit as n goes to infinity. These will need to multiply, so this goes up top, and this will go to the bottom. So this is going to be 2 times n plus 1 factorial times n factorial over n plus 1 factorial times 2n plus 1 factorial. What I'm going to do is I'm going to go ahead and simplify out what's in here. Right? So this 2 times n plus 1 would give us 2n plus 2 plus 1. So this is really just 2n plus 3 factorial. Okay, so I want to look at something real quick, which is what is 2n plus 3 factorial divided by 2n plus 1 factorial? Well, this would be 2n plus 3 times 2n plus 2 times 2n plus 1, and so on. And so then the rest of this is really just 2n plus 1 factorial. Right, so this would be 2n plus 1 factorial. And then we're dividing by 2n plus 1 factorial. So what this means is that we can cancel these out, and we'll just be left with 2n plus 3 times 2n plus 2. Okay. So that's how that works out. So let's go ahead and make that algebraic substitution, manipulation, magic, whatever you want to call it. So this is going to be 2n plus 3 times 2n plus 2. And that'll get rid of our 2n plus 3 factorial divided by 2n plus 1 factorial. And then n factorial over n plus 1 factorial, that will just give us n plus 1 on bottom. Well, we'll get a degree of 2 on top and a degree of 1 on bottom. So we know that this is going to go to infinity, which is, slightly bigger than 1. So this, our series diverges by the ratio test. And so for our next few examples, we're just going to be looking at, is the ratio test conclusive or inconclusive? Meaning, what this really says is when we calculate this limit that we've been calculating, is it equal to 1 or is it not equal to 1? If it's equal to 1, then we say that the ratio test is inconclusive. If it's not equal to 1, then we're getting that it's either divergent or absolutely convergent, which means that the ratio test is conclusive. Okay, so for this first one, we would get, we'll have the limit as n goes to infinity of, we're going to be taking an absolute value, so I'm going to ignore this negative 1 to the n, right? So we can say that the absolute value of a sub n, this would just be 1 over n. And the absolute value of a sub n plus 1, well, this would be 1 over n plus 1. So I'm going to use that because we can say that the absolute value of a sub n plus 1 over a sub n, this is the same thing as if you just take the absolute value of the top and divide by the absolute value of the bottom, right? And this works because of the properties of the numbers that we're using, as well as the fact that we're not going to be dividing by 0. Okay, so the absolute value of a sub n plus 1 on top, that'll give us 1 over n plus 1. The absolute value of a sub n on the bottom, that'll give us 1 over n. So this is going to be the limit as n goes to infinity of, this would be n over n plus 1, which is going to be equal to 1. So we say that the ratio test in this case is going to be inconclusive. So RT is inconclusive. Now let's look at example 10. So for example 10, we would get, the absolute value of a sub n would give us 1 over n factorial. The absolute value of a sub n plus 1 would give us 1 over n plus 1 factorial. So we'll have the limit as n goes to infinity of 1 over n plus 1 factorial over 1 over n factorial. So this is going to give me the limit as n goes to infinity of n factorial over n plus 1 factorial, which will give us the limit as n goes to infinity of 1 over n plus 1, which is going to be equal to 0. So we say that the ratio test is conclusive. And in fact, it tells us that this original series, if we proved that it was convergent to begin with, then we can say that this thing is absolutely convergent. Alright. Now for example 11, this will be our final example. We'll have, let's see, the absolute value of a sub n will give us n factorial over n plus 1 factorial. And the absolute value of a sub n plus 1 will give us n plus 1 factorial over n plus 1 factorial, so this is n plus 2 factorial. So we'll get the limit as n goes to infinity of, let's see, this is going to be n plus 1 factorial over n plus 2 factorial divided by n factorial over n plus 1 factorial. Okay, so this is the limit as n goes to infinity of, let's see, we'll have n plus 1 factorial times n factorial over n plus 2 factorial times n plus 1 factorial. And I just absolutely messed this up. This should be, sorry, should have kept track of these. So this goes to the bottom. This will go to the top. Okay. So then this should be n plus 1 factorial times n plus 1 factorial on top. And then we'll have n plus 2 factorial times n factorial on bottom. Okay. So the first thing I'm going to look at is what is n plus 1 factorial over n plus 2 factorial? Well, that would just give us 1 over n plus 2. So we'll have a n plus 2 on bottom, and then we'll have n plus 1 factorial divided by n factorial. So that'll give me an n plus 1 on top. And so then this, by L'Hopital's rule, is going to be equal to 1. So we can say that the ratio test is inconclusive. And this will conclude section 11.6. So I know we've been alternating between a bunch of different tests and a bunch of different series, but hopefully we're learning when we should apply which tests and when we shouldn't be applying certain tests. Have a great weekend.